Welcome back to Cosmos Unlocked. In the last video, after uncovering the surprising physical properties of space, its ability to warp, ripple, and expand, one question still stands: what kind of space do we actually live in? Is it flat, like the surface of a sheet of paper, or does it curve in on itself, like the surface of a sphere? In this video, we'll explore the implications of space's curvature, its possible size and shape, and the exciting mysteries that still surround the very fabric of the universe. Scientifically, we now have an answer: space does indeed appear to be flat, with an error margin of less than 0.4%. Scientists have reached this conclusion using two different methods. The first method involves measuring the sum of the angles in a triangle. We learned in school that in a flat space, the sum of the angles in a triangle is 180 degrees, while in a curved space, it is not. The scientists' method involved observing the early universe, finding three very distant points, and studying the spatial relations between them. The results confirm that space is flat. This is the first method. The second method is based on the origin of space curvature, which is the energy of the universe. General relativity suggests that a certain type of energy in the universe determines the direction of space curvature. In fact, the energy density measured is such that the space within our observable range does not curve. When we say that space is not curved, we mean that the error margin is within 0.4%. Saying that the space we live in is flat might sound unremarkable, but if you think about it carefully, it's quite a coincidence. Since the curvature of space depends on the amount of matter and energy in the universe, if there were even a little more matter and energy than now, space would curve in one direction. If there were a little less, space would curve in the other direction. Right now, the matter and energy in the universe seem to be just enough to keep space flat within the observable range. Specifically, this energy density is equivalent to about 5 hydrogen atoms per cubic meter. If there were 6 hydrogen atoms per cubic meter, or 4 hydrogen atoms per cubic meter, the universe is something completely different. What's even stranger is that the curvature of space can influence the movement of matter, and the amount of matter can, in turn, affect the curvature of space. This creates a positive feedback loop. In other words, if the universe had a little more or a little less matter in its early stages, the energy density in the universe today would not exactly maintain a flat space. It would cause the space to become increasingly uneven. The space we see today is flat, which means the universe was very flat in its early stages, or there may have been other mechanisms that helped maintain the flatness of space. This is one of the most mysterious properties of space. When discussing the essence of space, the question of its nature is not the only issue we face. Once you accept that space is not necessarily an infinite void, but more likely an infinite thing with physical properties, you can start asking various strange questions about it, such as, how large is space, and what shape does it have? Behind the size and shape lies the quantity and distribution of space. As we mentioned earlier, since space is flat, this implies it can extend infinitely, right? That seems intuitive. But not everything that seems intuitive is correct. Space may be flat and infinite, or it may be flat with boundaries, or even more bizarre, it could be flat and self-circular. How could space have boundaries? In fact, flat space does not have to be infinite. For example, the surface of a plate is a two-dimensional plane, but it also has a smooth, continuous boundary. Based on certain geometric properties at the boundary, three-dimensional space could also have boundaries. Even more interestingly, flat space could also be cyclical, much like in video games, such as Pac-Man. If you move a character off the right side of the screen, the character reappears on the left side. Space might have similar properties, and perhaps it can self-connect in a way we don't yet understand. General relativity predicted the existence of impulses where two distant locations in space could be connected actively. Is there some simple way to connect all the boundaries of space together? We don't know. Now, let's talk about quantum space. Just as pixels make up a TV screen, could space be made up of discrete little units, or is space infinitely smooth, with countless points between any two? Ancient scientists didn't think of air as being made up of tiny, discrete molecules. After all, air can fill any volume and has fascinating physical properties that can form wind and weather patterns. Now we know that everything about air, from the cool breeze on a summer day to the sensation of breathing smoothly, is actually the result of the combined motion of billions of air molecules. These properties are not inherent to individual air molecules. Space is similar. The theory of smooth space might sound more plausible because we try to glide through space, and the process feels easy and continuous. No one would experience something like a character in a video game jumping from one pixel to another with jerks, right? But can we be certain? Based on our current understanding of the universe, the concept of an infinitely smooth universe is actually more surprising. This is because we now know that, apart from space, everything else can be quantized, and quantum physics suggests the existence of a smallest quantized scale, about 10 to the power of -35 meters, known as the Planck length. From the perspective of quantum mechanics, space should also be quantized, though we don't know for sure. If space is quantized, then when we move through space, we are actually jumping from one region made up of tiny units to another. In other words, space can be seen as a grid composed of nodes connected together. It's similar to a subway system where each station represents a location and the connections between the stations represent the relationships between those places. This idea differs from viewing space merely as a representation of relationships between matter, because these nodes of space could exist even without matter. This is intriguing, because these nodes of space can exist independently. In this case, what we call space is actually the relationship between these points. Everything in the universe is essentially an attribute of space, not the element of space itself. For example, all matter could be a vibration mode of space nodes, which may sound a bit absurd, but it's actually not. Current theories are based on quantum fields that are ubiquitous in space. What is a field? It's a related value or number present throughout space. In string theory, strings are the excited states of these fields. The idea of quantizing space aligns with this concept. Physicists enjoy these far-reaching ideas because things that seem basic, like space, turn out to be much deeper than people thought. Some even speculate that the relationships between the nodes are due to quantum entanglement between particles, though this is still purely hypothetical. To sum up, here are the unsolved mysteries about space. 1. Space is a real thing, but what exactly is it? 2. Is the space we know all there is, or is there a larger space beyond it? 3. Are there regions in the universe without space? 4. Why is space exactly this flat? 5. Can space be quantized? Our ultimate question is, what is space for? Maybe, like air, space can have different states, and under extreme conditions, it might take forms we can't even imagine. Just like air has liquid, gas, and solid states, the form of space we are familiar with, the one we love and occupy, may just be one rare form among many. In other parts of the universe, other forms of space may exist, waiting for us to study and control. To answer this, we can use the most fascinating tool, the way mass and energy warp space. To understand what space is and what it can become, the best way is to observe it under extreme conditions. Imagine having the ability to witness the immense power of a black hole up close. These cosmic giants, with their massive gravitational pull, twist and distort the very fabric of space itself. The closer you get to one, the more extreme the forces become, stretching and compressing space in ways we can hardly comprehend. In the not-so-distant future, the possibility of observing this space-warping phenomenon could become a reality. Just recently, humanity achieved a remarkable feat. We captured the first-ever image of a black hole. This is a monumental step in our ability to observe and understand these mysterious objects that challenge the limits of our knowledge. But this is just the beginning. We're now able to detect gravitational waves, ripples in space-time caused by cataclysmic cosmic events like black hole collisions. These waves provide us with a unique window into the universe's most extreme phenomena. Who knows? With future advancements, we may even find ourselves exploring the vicinity of black holes firsthand, unlocking even more secrets about the very nature of space and time. As we continue our journey to explore the universe, the mysteries of space become more accessible than ever. Stay tuned, as next time on Cosmos Unlocked, we'll delve into the mysteries of time itself. Until then, keep looking up and stay curious.